50 years ago, physicists made a prediction. They said the first stars ever born in the universe would leave behind a very specific fingerprint. Helium radiation so intense it could only come from surfaces hotter than 100,000 degrees, paired with absolutely zero heavy elements. They said if we ever found that combination, we would be looking at the beginning of everything. No telescope had ever found it. Most astronomers quietly assumed none ever would. Then JWST captured a spectrum from 400 million years after the Big Bang, and sitting inside the data was the exact signal, the exact combination that had only ever existed in equations. If you are new here, welcome to Sundown Science. Hit like, subscribe, and get comfortable, because tonight I am going to show you how a faint spike of helium from 13.4 billion years ago connects directly to the atoms holding you together right now. Settle in and let's ease into it. Part 1. The detection that ends a 50-year hunt. There is a spike in the data that should not be there. It sits inside a spectrograph taken by the James Webb Space Telescope's near-infrared spectrograph instrument, a razor-thin emission line at a wavelength that corresponds to ionized helium. Helium that has been stripped of both its electrons by radiation so violent, so energetic, that almost nothing in the known universe can produce it. The line is sharp, it is intense, and it is alone. That last part is the problem. When astronomers look at the spectra of stars, galaxies, nebulae, anything that glows, they expect to see a crowd of signatures: carbon, oxygen, nitrogen, iron. These are the fingerprints of elements forged inside previous generations of stars, scattered into space when those stars died, and folded into whatever formed next. Every object we have ever studied in the cosmos carries at least a trace of these elements. Every single one. They are the universal contamination of a universe that has been recycling itself for over 13 billion years. But this signal has none of them. The helium emission is screaming, and the metal lines are silent, not faint, not buried in noise, absent, as if whatever produced this light exists in a universe where no star has ever died before, where no supernova has ever seeded the surrounding gas with heavier atoms, where the periodic table still has only 2 entries. And that combination, intense ionized helium emission plus 0 detectable metals, has never been recorded anywhere in the observable universe. Not in any galaxy, not in any nebula, not at any distance or redshift or epoch. Nowhere. Until now. To understand why this matters, you have to understand what astrophysicists have been chasing for more than half a century. Since the late 1960s, theoretical models have predicted that the very first stars to ever form in the universe, born from nothing but the hydrogen and helium left over from the Big Bang, would look fundamentally different from anything we see today. They would be massive, impossibly hot. They would burn through their fuel in just a few million years. And they would produce a very specific kind of radiation, the kind capable of ionizing helium a second time over, which requires photons carrying more than 54.4 electron volts of energy. These stars were given a name before anyone had ever seen one: Population 3. For 50 years, Population 3 stars have been the most important prediction in stellar astrophysics that has never been confirmed. We have built models, we have run simulations, we have searched through the spectra of the oldest, most distant objects we could find, and we have found nothing. Not one unambiguous detection, not one clean signature. They were the ghosts at the foundation of everything, necessary, predicted, and invisible, until the James Webb Space Telescope pointed its instruments at a small region near one of the most ancient galaxies ever observed and captured this signal. What the data shows is not just a single emission spike. There is a companion detection, a hydrogen gamma line, that confirms the helium signal is not an artifact, not a glitch, not an instrumental fluke. Two independent spectral features, both consistent with the same source, both pointing to the same conclusion. Something out there is producing radiation at temperatures exceeding 100,000 Kelvin, and it is doing so inside a region with no measurable chemical enrichment. But it gets stranger. The region where this signal was found does not contain just one component. It contains two, designated C1 and C2. C1 is chemically pristine, zero metals, consistent with gas that has never been touched by stellar evolution. C2 is slightly enriched. It carries faint traces of elements that could only have been produced by a previous generation of stars that already lived, burned, and exploded. Both components exist in the same region. Both are visible in the same data. Think about what that means. We are not just looking at a snapshot of the universe before stars existed, and we are not just looking at the universe after stars began polluting their surroundings with heavier elements. We are looking at both states, side by side, captured in the same observation. The before and the after, frozen in light that left its source over 13 billion years ago. The probability of catching this exact moment, the transition between a universe with no stellar chemistry and a universe where chemistry has just begun, is extraordinarily low. It is like finding a photograph of the exact second a candle was lit in a dark room, and in the same frame, seeing both the darkness and the first flicker of light. That does not happen by accident. It happens because something created the conditions for both states to coexist, and because an instrument happened to be precise enough, sensitive enough, and pointed in the right direction to capture it. That instrument is JWST, and this is not a coincidence. The James Webb Space Telescope was explicitly designed, from its mirror diameter to its orbital position to its infrared sensitivity, to find this signal. Population. 3 stars were one of the foundational science goals written into the mission from the beginning. This is what it was built to look for. And what it found is not just a star or a cluster or an anomaly in the data. What it found, if the interpretation holds, is the origin point. The moment the universe stopped being simple, the moment the first light ignited inside gas that had never been touched and began the chain of events that would eventually produce galaxies, planets, oceans, organic molecules, and everything made of anything heavier than helium, including you. But here is the thing that should keep you thinking. This signal was not found where anyone expected it. It was not inside a galaxy. It was found in a region just outside one, hovering at the edge of observability, as if the universe had tucked its most important secret in the last place we would think to look. And that is where the real mystery begins. Part 2. GN-Z11 and the Edge of Observability. The galaxy is called GN-Z11, and when you hear its redshift value, Z equals approximately 10.6, the number might not mean much on its own. So let me put it differently. The light JWST captured from this galaxy left its source roughly 400 million years after the Big Bang. It has been traveling through expanding space for approximately 13.4 billion years. When that light began its journey, the universe had existed for less than 3% of its current age. There were no spiral galaxies, no solar systems, no rocky planets. There was only the aftermath of the initial expansion, cooling gas, collapsing structures, and darkness. GN-Z11 is one of the most distant galaxies ever spectroscopically confirmed, and the fact that we can observe it at all is a testament to what modern instrumentation can do at the absolute limit. But let me be honest about something. When I say we observe GN-Z11, I do not mean we see a detailed portrait of a galaxy. JWST resolves it as only a handful of pixels. A few specks of ancient light smeared across a detector, redshifted so far into the infrared that without Webb's instruments it would be completely invisible. Everything we know about this galaxy comes not from its image, but from its spectrum, from the precise wavelengths of light it emits, stretched by the expansion of the universe into the narrow infrared window that JWST was designed to capture. And it is within that spectrum, at the edge of this galaxy, not inside it, that the helium emission signal was found. This is where the story takes its first truly strange turn. Star formation, as we understand it, happens inside galaxies. Gas collapses under gravity, fragments into clouds, and those clouds condense into stars. The process requires density. It requires structure. It requires a gravitational well, a region where enough mass has gathered to pull material inward. That is the inside of a galaxy, not the outskirts, not the space beyond its visible boundary. Yet the region producing the population 3 signal, the so-called HE region, sits outside the body of GN Z11. It is spatially offset from the galaxy itself, as though a pocket of gas somehow remained untouched, while everything around it was already forming stars and polluting its environment with metals. The leading hypothesis is that this represents a primordial gas cloud, a reservoir of hydrogen and helium that by chance or by geometry was never reached by the debris of earlier stellar deaths. It sat there, chemically pristine, while the universe around it began its long transformation. And then, something triggered it to collapse and form stars of its own. If that interpretation is correct, then we are looking at one of the most fortunate observational coincidences in the history of astronomy. A pocket of original, uncontaminated material caught in the act of producing stars for the very first time right next to a galaxy that has already begun its chemical evolution. It is the before and the after, sitting side by side 13.4 billion years ago. But GN Z11 has another surprise. This galaxy, despite existing at an epoch when the universe was barely beginning to assemble its first large structures, appears to host an active black hole, not a small one, a supermassive one, or at least one far more massive than anything we would expect to find this early. The presence of a black hole at this redshift raises its own cascade of questions, because black holes of this size typically require time to grow. They need to accumulate mass over hundreds of millions of years through accretion and mergers. Finding one this large, this early, means either our models for black hole growth are wrong, or something about the conditions in the early universe allowed black holes to form much larger, much faster than we thought. And now consider the picture forming around GN Z11. In this one system, one tiny smear of ancient light, we may be looking at multiple early universe processes happening simultaneously. First-generation star formation in a pristine gas cloud just outside the galaxy. Chemical enrichment already underway in an adjacent region. And a supermassive black hole that has no business being that large this early. Everything about this object is converging on the same conclusion. Whatever happened in the first few 100 million years after the Big Bang, it happened fast, it happened violently, and our models did not fully anticipate it. But I want to be careful here, because this is exactly the point where excitement starts to outrun evidence. GN Z11 exists at the absolute limit of what JWST can observe. The signals are faint. The spectral features are narrow. The spatial resolution, a few pixels, means that separating what belongs to the galaxy from what belongs to the surrounding region is an exercise in statistical precision, not direct imaging. When you are working at redshift 10.6, you are interpreting light that has been stretched, dimmed, and distorted by 13.4 billion years of cosmic expansion. Every measurement carries uncertainty. Every interpretation rests on assumptions about the physics of objects we have never seen before. So the question that hangs over this entire discovery is not just, did we find population 3 stars? It is something harder. Are we seeing clearly enough at this distance to be sure of what we are looking at? Can we distinguish a genuine signal from an artifact of the extreme conditions under which the observation was made? The answer to that question lives in the signal itself. in the specific physics that produced that screaming helium emission line. And those physics, it turns out, do not just point toward the first stars. They break almost every other explanation we have. Part 3. The signature that breaks astrophysics. Let me walk you through what it takes to produce the kind of helium emission detected in the HE region near GN Z11, because once you understand the physics, you will see why this signal has so few possible explanations. Helium is the second element on the periodic table. It has 2 protons and, in its most common form, 2 neutrons. Around that nucleus orbit 2 electrons. To ionize helium once, to strip away the first electron, you need a photon carrying at least 24.6 electron volts of energy. That is already a lot. It puts you solidly in the ultraviolet range, well beyond what visible light can achieve. But the signal detected near GN Z11 is not singly ionized helium. It is doubly ionized helium, helium-2, written as He, Roman numeral 2, which means both electrons have been ripped away, leaving a bare nucleus. To do that, you need photons exceeding 54.4 electron volts. That is extreme ultraviolet radiation, the kind produced only by the hottest, most energetic sources in the universe. We are talking about surface temperatures of at least 100,000 Kelvin, roughly 17 times hotter than the surface of our Sunday. Very few objects in the known universe can sustain those temperatures consistently enough to produce a strong, clean He2 emission line. Modern stars, the ones we observe in our galaxy and in nearby galaxies, generally do not produce this signature cleanly. Some hot, massive stars can ionize helium twice, but they always come with baggage. They show emission from carbon, nitrogen, oxygen, and other metals in their spectra. You cannot have a massive hot star in today's universe without those elements, because every star forming today does so from gas that has been recycled through multiple previous stellar generations. The raw materials are already contaminated. The periodic table is already full, but the HE region near GN Z11 shows no metals at all. This is the combination that breaks the pattern. Extreme ionizing radiation, the kind that requires absurdly hot sources, paired with a complete absence of any element heavier than helium. No carbon, no oxygen, no nitrogen, no iron. Nothing that would indicate this gas has ever been part of a star that died and spread its processed material into the surrounding medium. In astrophysics, the term for elements heavier than helium is metals. And yes, that includes things like carbon and oxygen, which no chemist would call a metal. It is an old convention, and it's stuck. The measure of how much of these elements a region contains is called metallicity. High metallicity means the gas has been enriched by many generations of stars. Low metallicity means fewer generations. Zero metallicity, or as close as we have ever measured, means no previous stars have contributed their fusion products to this gas. What the JWST data shows in C1, the pristine component of the HE region, is effectively zero metallicity. This is not just low, this is not just extremely metal poor, the label given to the oldest surviving stars in our own galaxy, which still carry trace amounts of iron and carbon from whatever came before them. This is a measurement consistent with gas that has never been inside a star, gas that still retains the original chemical composition set during the Big Bang, when the universe produced hydrogen, helium, and a tiny amount of lithium, and nothing else. Think about what that implies. We are looking at a region of space where the chemistry of the universe has not yet begun, where the only elements available are the ones baked into existence during the first few minutes after the Big Bang, during the process called Big Bang nucleosynthesis. Everything else, every atom of carbon in every organic molecule, every atom of oxygen in every glass of water, every atom of iron in every drop of blood, those came later. They came from stars. And in this region, no star has yet donated its products to the surrounding gas. This is not just rare. In the modern universe, it is impossible. Every cubic centimeter of interstellar space in our galaxy has been enriched by billions of years of stellar evolution. You cannot find a pristine region anywhere within millions of light years of us. The contamination is total and irreversible. The only place you could find gas this clean is in the very early universe, before the first stars had time to live and die and spread their contents, or in a pocket somehow shielded from that contamination for hundreds of millions of years. And that is exactly what the HE region appears to be. Now, here is why this matters for the central question. For decades, Population 3 models have predicted that the first stars, forming from pure hydrogen and helium, would be extraordinarily massive and extraordinarily hot, hot enough to produce exactly this kind of extreme ultraviolet radiation. The model said, if you ever find a region with zero metallicity and strong He2 emission, you are looking at the first generation. That was the prediction. It was specific. It was falsifiable. And the JWST data matches it. But the match does not end with C1. Remember C2, the second component, slightly enriched with metals. C2 represents the next step. It is gas that has already been touched by the death of at least one previous star. Its metals are faint, but they are there, meaning that somewhere nearby, a star already formed from pristine material burned through its fuel and exploded, seeding its surroundings with the first heavy elements the universe had ever produced. We are watching the moment that chemistry, real chemistry, the kind that eventually leads to molecules and minerals and planets and life, switches on for the first time. C1 is the universe before. C2 is the universe after, and both are sitting in the same field of view, separated by a few pixels on a detector orbiting 1 million miles from Earth. The question now is, what kind of stars could possibly produce this? What burns this hot, this bright, this briefly, and dies so violently that it seeds its entire neighborhood with new elements before anything else has time to form? The answer takes us into a kind of physics that has no equivalent anywhere in the universe today. Part 4. The transition point, C1 versus C2. The two components are not just chemically different, they are moving differently. Spectral analysis of the HE region reveals a velocity separation between C1 and C2 of approximately 120 kilometers per second. That is not a small number. For context, the International Space Station orbits Earth at about 7.7 kilometers per second. A bullet fired from a high-powered rifle travels at roughly 1 kilometer per second. The two components of this detection are flying apart or moving relative to each other at a speed that suggests they are not passive, static clouds of gas gently drifting through space. They are part of a dynamic, physically structured system. This velocity offset tells us something important. C1 and C2 are likely distinct clumps within a larger region, a cluster of gas and forming stars, where different pockets have reached different stages of chemical evolution. C1, with its zero metallicity, is still in its original state, untouched by any stellar byproduct. C2 has already been contaminated. Something within or near C2 has already formed, burned, died, and expelled heavy elements into its surrounding material. And the two components are close enough to be captured in the same spectral observation, yet separated enough in velocity space to be distinguished. What this paints is a picture of clustered star formation, not a single isolated primordial star igniting alone in the void, but a region where multiple gas pockets are collapsing and forming stars nearly simultaneously, each at its own pace. Some have already produced their first generation and are now being enriched by the debris. Others are still pristine, still forming stars from uncontaminated material. The whole region is caught in a cascade of birth, death, and transformation, happening so fast that both the beginning and the intermediate stages are visible at once. And that speed is significant. If the first stars in this region formed, lived their entire lives, and died, all within a time window short enough for both the pristine and the enriched gas to coexist, then those stars burned through their fuel extraordinarily quickly. That is consistent with what population 3 models predict: massive stars with lifespans measured in just a few million years, possibly less. A star with 100 times the mass of our Sun does not get billions of years. It gets maybe 2 or 3 million. A star with 1,000 solar masses might last even less. They ignite, they blaze, they die, and they die violently enough to pollute their surroundings almost immediately. This challenges a certain intuition about the early universe. You might imagine that the first stars appeared, burned for a while, and that the chemical enrichment of the universe was a slow, gradual process, a gentle drift from pure hydrogen and helium toward the complex chemistry we see today. The C1-C2 split suggests otherwise. The enrichment began almost as soon as the first stars did. The gap between no metals anywhere and metals already present in neighboring gas was not hundreds of millions of years. It may have been just a few million. The universe went from chemically empty to chemically active in what amounts to a blink. This also strengthens the idea that first-generation star formation was not a scattered, isolated phenomenon. It was clustered, multiple stars forming together in the same region from the same general reservoir of gas, some igniting first, dying first, and contaminating their neighbors, others igniting slightly later, still burning from pristine fuel even as the first enrichment wave was already propagating outward. The HE region is not showing us one first star. It may be showing us an entire first generation, a nursery where the universe's earliest and most extreme stars were born, lived, and died in rapid succession. And the implications cascade from here. If the first stars formed in clusters, then their combined ultraviolet radiation would have been enormous, enough to ionize the surrounding hydrogen gas across a significant volume. Their combined supernovae would have injected heavy elements not into one small pocket, but into a wide region, jump-starting the chemical complexity needed for the next generation of stars. The transition from a simple universe to a complex one was not a gradual fade. It was a detonation. We are watching that detonation, preserved in the spectrum of the HE region. The moment the universe shifted from simplicity to complexity, from a cosmos with only 2 usable elements to one where the raw materials for everything, stars, planets, water, amino acids, were being manufactured for the first time. But to truly understand what these first stars were, and why nothing like them exists today, we need to understand how the universe classifies its stars, and that system, it turns out, is numbered backwards. Part 5. Stellar populations and the backward naming problem. In the 1940s, an astronomer named Walter Bayade noticed something peculiar while studying the Andromeda galaxy. He realized that not all stars were the same age or composition. Some were young, hot, and loaded with heavy elements. Others were old, cooler, and had far fewer metals. He sorted them into 2 groups. The young, metal-rich stars became population 1. The old, metal-poor stars became population 2. The numbering was based on the order of discovery, not the order of appearance. Population 1 was named first, because those were the stars we encountered first. They are all around us, in the disk of the Milky Way, easy to study. Population 2 came next, found in the galaxy's halo and in globular clusters, relics of a much earlier epoch. But it did not take long for theorists to realize there had to be a third group. If population 2 stars are old and metal-poor, something must have come before them. Something that produced the small but measurable traces of metals found in even the most ancient population 2 stars. You cannot have slightly enriched without something doing the enriching first. There had to be a generation 0, a population of stars that formed from completely pristine material and created the first heavy elements through fusion and violent death. That group was named Population 3. Third to be proposed, first to exist. It is the kind of naming convention that only makes sense if you know the history, and it has confused students and science enthusiasts for decades. But the classification is not arbitrary. Metallicity, the proportion of elements heavier than helium, is genuinely a generational marker. It tells you where a star sits in the lineage of cosmic chemistry. Population. 1 stars, like our Sun, are late generation. They formed from gas enriched by billions of years of stellar processing. Population 2, stars formed earlier, from gas with fewer contributions. Population. 3 stars, if they existed, formed from gas with no contributions at all. They are the origin. Everything else descends from them. And this framework is exactly what allows the JWST signal to be interpreted at all. When astronomers see the head-to emission from the Hetchy region with zero metallicity, they are not guessing. They are applying a classification system that connects chemical composition to stellar generation. Zero metals means first generation. First generation means population 3. The signal fits the framework like a key in a lock, which is either deeply confirming or, if you are a careful scientist, slightly worrying, because nature does not always cooperate with our categories. Before JWST, the best indirect evidence for population 3 stars came from what you might call proxy stars, extremely metal-poor stars found in the halo of our own galaxy, with iron abundances less than 1/10,000th of the Sun's. These stars are not population 3 themselves. They contain metals, which means they formed after the first generation had already died. But they are so metal-poor that they likely formed in an environment only lightly enriched by a single previous supernova. They are the children of population 3, carrying just enough of their parents' chemical fingerprint to hint at what came before. What JWST has done is leap from indirect evidence to something approaching direct detection, not a descendant star bearing faint traces. An actual region, at the right distance, at the right epoch, producing the right signal with the right chemistry. The gap between proxy evidence and primary observation has just narrowed dramatically, and the classification system that Walter Baade started in the 1940s is the reason we can read the signal at all. Now, the framework tells us these first stars existed. The signal tells us we may be seeing their light. But what were they actually like? What kind of star forms from nothing but hydrogen and helium? And why would it look so radically different from everything burning in the sky today? The answer lies in a single missing ingredient and the catastrophic consequences of not having it. Part 6. The physics of population 3 stars. Every star you have ever seen, every point of light in the night sky, every star catalogued in every survey, every sun orbited by every known exoplanet, formed from gas that contained metals, carbon, oxygen, silicon, iron. These elements, even in small amounts, play a critical role during star formation because they are efficient at radiating away heat. When a cloud of gas begins to collapse under its own gravity, it heats up. That heat creates pressure which pushes back against the collapse. If the gas cannot cool itself down, the collapse stalls. The cloud just sits there, hot and puffy, and no star forms. Metals solve this problem. Carbon and oxygen atoms, even in trace quantities, can absorb thermal energy and re-emit it as infrared photons, which escape the cloud. The cloud cools. The pressure drops. The collapse continues. Smaller fragments break off. Each fragment condenses further, heats up again, and eventually reaches temperatures high enough to ignite nuclear fusion. A star is born, and because the fragmentation process divides the cloud into many pieces, the result is usually a collection of stars with a wide range of masses, some large, some medium, some small. This is called the initial mass function, and in the modern universe, it favors modest stars. Most stars forming today are red dwarfs, with masses less than half that of our Sun. Now remove the metals entirely. In the very early universe, before any star had ever died and spread its processed elements into the surrounding gas, the only available materials were hydrogen, helium, and trace amounts of lithium. These elements are terrible at radiating heat. Hydrogen molecules can cool gas to a few hundred Kelvin, but below that, they stall. The gas remains hotter than it would be in a metal-enriched environment. The pressure stays higher. The collapsing cloud cannot fragment as effectively. The result is fewer, larger fragments. Instead of a cloud breaking into dozens or hundreds of pieces, each producing a modest star, the cloud breaks into a handful of massive clumps. Each one collapses into a single enormous star. The initial mass function is top-heavy, meaning it is skewed dramatically toward high-mass stars. While today's universe favors stars less massive than the Sun, the primordial universe likely favored stars tens, hundreds, or even 1,000 times more massive. And this connects directly back to the signal detected near GN Z11, that screaming helium-2 emission, which requires radiation exceeding 100,000 Kelvin, is exactly what you would expect from stars this massive. A star with 100 solar masses has a surface temperature several times hotter than our Sun. A star with several hundred solar masses pushes past 100,000 Kelvin and into the regime where it can ionize helium twice over with its ambient radiation. These are not ordinary stars. They are furnaces of a kind the universe no longer builds. Their luminosities would have been staggering. A single population 3 star with a few hundred solar masses would have outshone our entire Sun by a factor of millions. A cluster of them, which is what the C1 and C2 components suggest, would have lit up the surrounding gas like a searchlight punching through fog. The ultraviolet radiation pouring out of such a cluster would have been intense enough to ionize hydrogen and helium across a region many light-years wide. And that radiation is precisely what we detect as the He2 emission line in the JWST data. But mass comes with a price. In stellar physics, the more massive a star, the shorter its life. Our Sun will burn for roughly 10 billion years. A star with 10 solar masses lasts about 20 million. A star with 100 solar masses might last 2 or 3 million years, and a star with 1,000 solar masses, if such a thing existed, would exhaust its fuel in perhaps 1 million years or less. These first stars were not long-lived beacons. They were brief, incandescent flares, and their deaths were unlike anything in the modern universe. For the most massive population 3 stars, those above roughly 130 solar masses, but below about 260, the physics of their cores leads to a phenomenon called pair instability. At extremely high temperatures, the gamma-ray photons inside the star's core begin converting into pairs of electrons and positrons. This is not hypothetical. It is a well-understood quantum mechanical process, but it has a devastating consequence. Those gamma rays were providing radiation pressure, holding the star up against its own gravity. When they convert into matter, the pressure drops. The core contracts. The contraction raises the temperature further, which triggers even more pair production, which drops the pressure even more. The star enters a runaway collapse. In some mass ranges, this runaway does not stop at a bounce. The entire star detonates. Not a core collapse supernova, where the outer layers are blown off while the core remains as a neutron star or black hole. A pair instability supernova obliterates the star completely. Every atom that was inside it, every bit of hydrogen that was fused into helium, every nucleus of carbon and oxygen and silicon built up during its brief life, gets ejected into space at thousands of kilometers per second. Nothing is left behind. No remnant. No core. Just an expanding shell of the first heavy elements ever made, racing outward into a universe that has never seen them before. For stars even more massive than that threshold, the collapse is so total that no explosion occurs. The star simply falls into itself and forms a black hole directly, swallowing most or all of its processed material. No supernova, no chemical enrichment, just a black hole appearing where a giant star used to be. Both pathways matter. The ones that explode are the ones that seed the universe with metals, kick-starting the chemical enrichment that C2 has already begun to show. The ones that collapse may explain how supermassive black holes, like the one apparently lurking inside GN Z11, could appear so early in cosmic history. Both are consequences of the same population of extreme stars, and both connect back to the signal. The He2 emission confirms radiation from sources hot enough to be population 3. The split between pristine and enriched gas confirms that some of those sources have already died. The velocity structure suggests a cluster, not an isolated event. Everything fits a scenario where massive, short-lived, first-generation stars formed together, burned briefly and brilliantly, and then began dying in ways that transformed their surroundings almost immediately. These stars were the first engines of change. They converted the simplest possible universe into one with actual chemistry. And the proof of that conversion, the debris of their deaths, is what we now need to look at more closely. Part 7. The first supernovae and nucleosynthesis. Every atom of carbon in your body was built inside a star. Every atom of oxygen you are breathing right now was forged in a stellar core and expelled into space when that star ran out of fuel. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all of it was manufactured through nuclear fusion, deep inside objects that no longer exist, and scattered across space by explosions that happened billions of years before the Earth formed. This process is called nucleosynthesis, and it follows a strict sequence. A star begins by fusing hydrogen into helium in its core. When the hydrogen runs out, if the star is massive enough, it compresses the helium and fuses it into carbon. Then carbon into oxygen, oxygen into silicon, silicon into iron. Each stage burns hotter, lasts shorter, and produces a heavier element. Iron is the end of the line. Fusing iron consumes energy rather than releasing it, so the process stops. In massive stars, this creates an inert iron core that eventually collapses, triggering the supernova that blasts everything above the core into the surrounding space. But here is the point that ties this directly to the JWST discovery. Before population 3 stars, this process had never happened, not once. The universe had hydrogen, helium, and a whisper of lithium, and that was all. No carbon, no oxygen, no iron. The entire chain of nucleosynthesis that produces every element necessary for planets and chemistry and biology. That chain had a beginning, and that beginning was the moment the first massive star exhausted its fuel and either exploded or collapsed. The pair instability supernovae of population 3 stars would have been the most chemically productive explosions in the history of the universe. Because these stars were so massive, they processed enormous quantities of material through the full fusion chain before detonating. A single pair instability supernova from a 200 solar mass star could eject tens of solar masses of heavy elements, carbon, oxygen, magnesium, silicon, in a single event. That material would expand outward, mixing with the surrounding pristine gas, raising its metallicity from 0 to something measurably above 0 for the first time. And that is exactly what C2 represents. The slightly enriched component of the HE region is gas that has already received its first dose of metals from a nearby supernova. The enrichment is faint, far below what you would find in even the most metal-poor stars in our galaxy today, but it is there. It is the chemical fingerprint of the very first stellar deaths, caught in the act of contaminating their surroundings. Once that contamination begins, everything changes. Gas with even a tiny fraction of metals can cool more efficiently. It fragments into smaller pieces when it collapses. The stars that form from it are smaller, less extreme, longer-lived. Population: 2 stars emerge, still old, still metal-poor by modern standards, but fundamentally different from the giants that preceded them. The initial mass function shifts. The era of 1,000 solar mass monsters is over. The era of stars like those we know begins. The JWST signal captures the exact hinge point. C1 is the last instant before chemistry. C2 is the first instant after. And the elements released in those first supernovae, scattered into a universe that had never contained them, are the same elements that would eventually accumulate, generation after generation, until they became part of rocky planets, liquid water, and the molecular structures that make biology possible. Every atom heavier than helium in your body passed through at least one star, and the first stars to ever perform that transformation, the ones that initiated the entire chain, appear to be exactly what JWST has found at the edge of GN Z11. But these stars did not just change the chemistry of the universe, they changed its visibility. Part 8. Cosmic Dawn and Reionization. For roughly the first 380,000 years after the Big Bang, the universe was opaque. Not dark, it was glowing with thermal radiation, but opaque in the sense that light could not travel freely. The cosmos was a dense, hot plasma of protons, electrons, and photons, all tangled together. Photons could not move more than a short distance before colliding with a free electron and scattering. The universe was, effectively, a wall of fog. Then the plasma cooled enough for electrons to combine with protons and form neutral hydrogen atoms. This event, called recombination, made the universe transparent for the first time. The photons that were released at that moment have been traveling ever since. We detect them today as the cosmic microwave background, the oldest light in the universe. But transparency did not last. Once neutral hydrogen filled the cosmos, it absorbed most ultraviolet and visible light. The universe entered what astronomers call the cosmic dark ages, a period lasting hundreds of millions of years during which no stars existed, no significant light sources were shining, and the only radiation was the fading afterglow of recombination, redshifting into the microwave band as the universe expanded. The Dark Ages ended when the first stars ignited and began emitting ultraviolet radiation powerful enough to ionize the surrounding hydrogen, stripping electrons from atoms and making the gas transparent again. This process is called reionization, and it transformed the universe from an opaque, neutral medium back into the ionized plasma that fills intergalactic space today. It was, in effect, the universe turning the lights on for the second time. And this is where the population 3 connection becomes direct. Reionization requires enormous amounts of ultraviolet radiation. The sources responsible had to be prolific emitters of photons above 13.6 electron volts, the ionization energy of hydrogen. Population: 3 stars, with their extreme temperatures and massive luminosities, are among the most efficient producers of such photons ever theorized. A cluster of massive first-generation stars could ionize a volume of space millions of light-years across. And the JWST data, showing extreme He2 emission from a region consistent with pristine or near-pristine star formation, supports exactly this picture. The detection near GN Z11 places this activity at approximately 400 million years after the Big Bang, right in the epoch when reionization is believed to have been underway, but not yet complete. The first stars detected by JWST are not just the first chemical engines. They may also be the sources that burned away the neutral hydrogen fog and made the universe observable. Without them, light from distant galaxies would have been absorbed before it ever reached us. Without them, the universe would still be dark. The stars that JWST may have found did not just exist, they remodeled the cosmos. They changed what could be seen. And now, having established what they were, and what they did, we have to face the harder question, the one that separates discovery from knowledge. Can we be sure this is what we are actually looking at? Part 9. The Black Hole Alternative. GN Z11 hosts an active black hole, and black holes are well known for producing high-energy radiation. As matter spirals into a black hole's accretion disk, it heats up to extreme temperatures and emits radiation across the electromagnetic spectrum, including the ultraviolet range. So, it is fair to ask, could the He2 emission detected in the He region come not from population 3 stars, but from the black hole's radiation field? The short answer, based on current modeling, is probably not. The He2 emission observed is stronger than what accretion models predict for a black hole at this distance and luminosity. The spatial offset, the fact that the signal comes from outside the galaxy, not from its center, also makes a black hole origin difficult to reconcile with standard accretion geometry, and the absence of other spectral signatures typically associated with active black holes further weakens the case. The black hole hypothesis cannot be completely eliminated, but it does not fit the data as cleanly as the stellar interpretation. There is a more speculative version of this alternative, primordial black holes, hypothetical objects that formed not from stellar collapse, but from density fluctuations in the very early universe. These remain unconfirmed and would require new physics to explain the observed signal. For now, the stellar explanation holds. Part 10. Wolf-Rayet stars ruled out. Now, before we move on, there is one more alternative that needs to be addressed, and honestly, this one is the most interesting to rule out, because at first glance, it looks like a genuinely strong candidate. If you have spent any time reading about extreme stars, you may have come across a class of objects called Wolf-Rayet stars. And if you have, you might be thinking, could those explain the signal near GN Z11 without needing to invoke population 3 stars at all? It is a fair question. So let me walk you through why the answer is almost certainly no, and why the process of elimination itself tells us something important about what we are actually looking at. Wolf-Rayet stars are, by any measure, among the most extreme stellar objects in the modern universe. They are massive, typically starting their lives at 20 or more solar masses. They are ferociously hot, with surface temperatures that can exceed 100,000 Kelvin, putting them in the same thermal neighborhood as the sources we need to explain the He2 emission near GN Z11, and they are violent. Unlike most stars, which hold on to their outer layers for the majority of their lives, Wolf-Rayet stars strip themselves bare. Intense radiation pressure and powerful stellar winds blast their outer hydrogen envelopes away, exposing the superheated core directly to space. What you are left with is essentially a naked stellar engine, a blazing ball of processed material radiating at extraordinary intensities across the ultraviolet spectrum. Because of these properties, Wolf-Rayet stars produce some of the strongest emission features of any stellar class. Their spectra are distinctive and dramatic, broad, bright emission lines that dominate the ultraviolet and optical wavelengths. And some of those emission features, at least superficially, resemble what was detected in the He region: strong helium emission, intense ultraviolet output, the thermal profile of an object running at temperatures most stars never reach. So, on the surface, you might look at the JWST data and think, could a cluster of Wolf-Rayet stars sitting in or near GN Z11 be producing this signal? Could we be mistaking a known type of extreme star for an unknown one? Here is where it falls apart, and it falls apart completely. Wolf-Rayet stars always contain metals. Always. This is not an occasional characteristic or a statistical tendency. It is a definitional feature of what they are. Wolf-Rayet stars are not young, primordial objects forming from pristine gas. They are evolved, late-stage phases in the lives of massive stars that have already burned through significant portions of their nuclear fuel. By the time a star enters the Wolf-Rayet phase, it has fused hydrogen into helium, helium into carbon, carbon into nitrogen and oxygen. Its exposed core is a showcase of processed elements, and its spectrum reflects this without exception. When astronomers observe Wolf-Rayet stars, they see strong, broad emission lines of carbon, nitrogen, and oxygen, often so prominent that Wolf-Rayet stars are subdivided into categories based on which of these elements dominates their spectra. WC stars show strong carbon lines. WN stars show strong nitrogen lines. WO stars, the rarest, show oxygen. There is no version of a Wolf-Rayet star, in any observation ever made, in any galaxy, at any distance, that lacks these metal signatures. They are baked into the physics of what a Wolf-Rayet star is, and the HE region near GN, Z11, shows none of them. 0 carbon, 0 nitrogen, 0 oxygen, 0 iron. The metallicity measurement of C1, the pristine component, is consistent with gas that has never been processed through a star. This is not a case of the metals are faint. It is not a case of the metals might be there, but below the detection threshold. The upper limits are extraordinarily low, consistent with truly primordial material, and that single fact disqualifies every known type of Wolf-Rayet star from being the source of the He2 emission. Think about what this means in practical terms. To explain the JWST signal with Wolf-Rayet stars, you would have to propose the existence of a completely new class of stellar object, a Wolf-Rayet analog that somehow achieves the same extreme temperatures, the same intense ultraviolet output, and the same spectral characteristics, but without any metals in its atmosphere or its surrounding medium. A metal-free Wolf-Rayet star. Nothing like this has ever been observed. Nothing like this has ever been predicted by stellar evolution models. You would essentially be inventing a hypothetical object from scratch with no independent evidence for its existence, solely to avoid the conclusion that the signal comes from population 3 stars. Compare that to the alternative. Population 3 stars, massive, hot, primordial, have been predicted by theoretical models for over 50 years. Their expected spectral signatures have been calculated in detail. The conditions under which they would form, from pure hydrogen and helium gas in the early universe before chemical enrichment, are well understood. The He2 emission with 0 metals is exactly, specifically, precisely what those models said we should find if we ever managed to observe one. No new physics is required. No unknown stellar class needs to be invented. The signal matches a prediction that has been sitting in the astrophysics literature since the 1970s. In science, when you have 2 competing explanations, one that requires inventing something entirely new and unsupported, and one that confirms a well-established, decades-old prediction, the principle of parsimony tells you which one to take seriously. You do not choose the explanation that multiplies unknowns without justification. You choose the one that fits the existing framework with the fewest additional assumptions. And that, overwhelmingly, is population 3. But I want to be careful here, because ruling out Wolf-Rayet stars is not the same as proving population 3. It is one more alternative eliminated, one more door closed, one more line of maybe it is something else crossed off the list, and the cumulative effect of these eliminations is significant. The black hole alternative struggles to match the emission intensity and spatial offset. Wolf-Rayet stars cannot explain the absence of metals. Known stellar populations at any metallicity do not produce this exact combination of features. One by one, the alternatives fall away, and what remains is the explanation that was predicted before the telescope was even launched. That is a powerful position for any scientific claim to be in. But it is not proof. Consistency with a prediction is not the same as confirmation. The history of astronomy is full of signals that look definitive right up until the moment they were reinterpreted, revised, or retracted. We have been here before, standing at the edge of a breakthrough, holding data that seems to match our best models, feeling the gravitational pull of a discovery we desperately want to be real. And sometimes it is real. And sometimes the universe turns out to be doing something we had not considered. The elimination of Wolf-Rayet stars and the weakness of the black hole alternative leave population 3 as the most consistent interpretation of the JWST signal. The data fits, the models align, the prediction is satisfied, but the distance is extreme, the signal is faint, and the region is resolved in only a handful of pixels. We are reading the universe's most important story from its most difficult handwriting. And that tension between what the data strongly suggests and what the scientific process demands before declaring victory is where this discovery lives right now, not in certainty, not in doubt. Somewhere in between, where the most interesting science always happens. Part 11. The bias problem. I want to be honest about something uncomfortable, because this is where the excitement of discovery runs headfirst into the machinery of human psychology. And if we are going to take this detection seriously, if we are going to treat it with the respect it deserves, then we have to talk about the one thing that could undermine it from the inside. Not bad data, not instrument failure, not an alternative astrophysical source. Something much harder to control. Us. The James Webb Space Telescope was designed, in part, to find population 3 stars. This was not a secondary objective buried in an appendix somewhere. It was written into the mission science case from the beginning. When engineers decided on the diameter of the primary mirror, 6.5 meters of gold-coated beryllium, one of the calculations that justified that size was the ability to collect enough photons from the most distant, faintest objects in the universe to detect spectral signatures from the first generation of stars. When they chose the wavelength range for the near-infrared spectrograph, the instrument that captured the He2 emission near GN Z11, the decision was shaped by the expected redshift of objects from the first few 100 million years after the Big Bang, exactly the epoch where population 3 stars would have formed. When they selected the orbit at Lagrange point 2, 1.5 million kilometers from Earth, the thermal stability of that location was chosen partly to ensure the exquisite sensitivity needed to detect signals this faint and this ancient. Every layer of the telescope's design carries the fingerprint of this goal. The people who built it knew what they were looking for. The people who planned the observations knew what they were looking for. And the people who analyzed the data, the ones who identified the He2 emission, measured the metallicity and published the interpretation, they knew what the expected signal should look like, because they had spent their careers studying the models that predicted it, and when they found a signal that matched those models, they identified it accordingly. Now, I need to be very clear about something. This is not a flaw in the scientific process. It is the scientific process. You cannot build a telescope to detect something unless you first predict what that something should look like. You cannot design an instrument sensitive to a specific spectral feature unless you know which spectral feature to target. Prediction comes before observation. Hypothesis comes before test. That is how science works. And it is the reason science works. The alternative, building instruments randomly and hoping to stumble across something meaningful, is not a methodology, it is a lottery. But the same structure that makes science powerful also makes it vulnerable to a very specific failure mode. Confirmation bias, the well-documented tendency for human beings to interpret ambiguous evidence in favor of a hypothesis they already hold, is not a fringe concern in situations like this. It is a central one. When you have spent years or decades predicting a signal, designing an instrument to find it, and then analyzing data specifically to detect it, the psychological pull towards seeing it, even in marginal or ambiguous data, is enormous. Not because the scientists are careless, not because they are dishonest, because they are human, and human brains are pattern-matching machines that preferentially match patterns they have been primed to expect. The history of astronomy is full of cautionary tales on this exact point, and it is worth pausing on a couple of them, because they illustrate the dynamic perfectly. In 1967, a graduate student named Jocelyn Bell Burnell was analysing data from a radio telescope at Cambridge when she noticed a repeating signal, a pulse arriving with clockwork regularity every 1.337 seconds from a fixed point in the sky. Nothing natural, as far as anyone knew, produced a signal that precise. Her supervisor, Anthony Hewish, and the rest of the team were intrigued enough to give it a half-joking designation, LGM1, for Little Green Men. The implication was playful but revealing. The signal was so unexpected, so clean, that the initial frame of interpretation drifted toward the extraordinary. It turned out to be a pulsar, a rapidly rotating neutron star emitting beams of radiation like a cosmic lighthouse. A natural object, not an artificial one. But for a brief window, what the observers wanted to be true shaped how they talked about what they had found. More recently, and more painfully, the BICEP 2 experiment provides what is probably the most instructive parallel to the current situation. In 2014, a team using a telescope at the South Pole announced that they had detected a specific pattern in the polarization of the cosmic microwave background, a swirling signature called B-mode polarization, which, if genuine, would have been direct evidence of gravitational waves generated during cosmic inflation, the hypothesized exponential expansion of the universe in its first fraction of a second. The announcement was enormous. It made front-page news worldwide. Press conferences were held. Congratulations poured in. Some physicists openly discussed Nobel Prizes. Months later, a joint analysis with data from the Planck satellite revealed that the signal was contaminated, possibly dominated, by thermal emission from interstellar dust in our own galaxy. The dust produced a polarization pattern that mimicked the expected inflationary signal closely enough to fool the initial analysis. The detection was effectively retracted. The prediction of inflationary gravitational waves remains unconfirmed to this day. The BICEP 2 team was not incompetent. They were among the best observational cosmologists in the world, using state-of-the-art instrumentation, applying rigorous statistical methods. And they still got caught by the combination of a faint signal, a confounding source they had underestimated, and the immense psychological and professional pressure to deliver the result their field had been waiting for. The population 3 detection near GN Z11 lives in this same territory. The signal is real, that much is not in dispute. The He2 emission is present in the data, and it is confirmed by a companion hydrogen gamma detection that rules out simple instrumental artifacts. A separate peer-reviewed study, conducted independently, reaches a consistent interpretation. These are meaningful safeguards. They elevate this detection well above the level of a preliminary or speculative claim. But safeguards are not the same as proof. This is still a single detection, one signal from one region near one galaxy at the extreme boundary of what JWST can observe. The source is resolved in only a few pixels. The spectral features, while consistent with population 3 models, are being extracted from data at redshift 10.6, a regime where noise is high, where calibration uncertainties are significant, and where the difference between a genuine astrophysical signal and a systematic artifact can be agonizingly subtle. To move this from strongest candidate in the history of the search to confirmed detection, the scientific community needs something it does not yet have: replication. Another pristine He2 emitting region, found near a different galaxy at a different redshift, observed through an independent program and analyzed by a separate team. If the population 3 interpretation is correct, then these regions should exist elsewhere, other pockets of primordial gas caught in the act of forming first-generation stars at other locations across the early universe. Finding even one more would dramatically strengthen the case. Finding several would effectively close it. Without that replication, the interpretation remains provisional, not wrong, not weak. Provisional, which is the scientifically honest way of saying, this is the best explanation we have, and we are not yet certain it is the right one. And I want to emphasize, this is not a failure. This is not something to be frustrated by. This is how science is supposed to work at the frontier. The first detection opens the door. Confirmation walks through it, and the researchers involved, to their genuine credit, are careful about this distinction. The published papers present the population 3 interpretation as the most consistent explanation for the observed data, not as established fact. They enumerate the alternatives. They quantify the uncertainties. They explicitly call for follow-up observations. This is what responsible science looks like when the stakes are this high, because the stakes are extraordinary. If this detection is confirmed, it is not just another discovery. It is the identification of the first stars that ever existed, the objects that initiated the chemical evolution of the entire universe. The emotional and historical weight of that claim is almost without precedent in observational astronomy. And when a claim carries that much weight, the bar for acceptance must be correspondingly high. The bigger the implication, the stronger the evidence needs to be. That is not a bureaucratic hurdle. It is a principle that protects the integrity of every discovery that clears it. The tension between what we want this signal to be and what the data can currently prove is one of the most important dynamics playing out in astrophysics right now. It is the tension that separates excitement from knowledge, enthusiasm from understanding, and it is a tension that, for now, remains unresolved. And yet, and this is the part I keep coming back to, there is something about this detection that resists easy dismissal. It is not just the He2 emission. It is not just the zero metallicity. It is not just the match with 50-year-old theoretical predictions. It is something else entirely. Something about the location of the signal, a detail that, the more you think about it, becomes the strangest part of the entire story. Part 12. The location anomaly. The most unusual thing about the population 3 candidate signal is not its chemistry or its temperature or its redshift. It is its address. The He region, the source of the screaming helium emission with zero metals, sits outside GN Z11, not at its center, not embedded within its disk or its densest star-forming regions, not tucked into the gravitational core where you would expect the most intense activity to occur. It is offset from the galaxy's main body by a measurable angular distance, sitting out in a region that, according to every standard model of how stars form, should not be forming stars at all. And this detail, which might sound like a minor technical footnote, is actually the strangest part of the entire discovery, because the location does not just challenge our interpretation of this particular signal. It challenges our understanding of how the early universe assembled itself. Let me explain why. Star formation, as we understand it, is fundamentally a story about gravity winning a fight. You start with a cloud of gas. That gas has thermal energy, it is warm, and that warmth creates pressure that pushes outward, resisting collapse. For a star to form, gravity has to overcome that pressure. The gas has to accumulate in sufficient density, in a region with a strong enough gravitational pull that the inward force wins and the cloud collapses. This process, in the modern universe, happens inside galaxies. It happens in molecular clouds, dense, cold regions within galactic disks where gas has been funneled by spiral arm dynamics and gravitational focusing. It happens in galactic cores where mass concentrations are highest. It happens, occasionally, in satellite structures orbiting larger galaxies. It does not typically happen in the diffuse, low-density space at a galaxy's extreme outskirts. Out there, the gas is too thin. The gravitational well is too shallow. There is nothing to drive collapse, nothing to concentrate material, nothing to push a cloud past the threshold where gravity takes over and fusion becomes inevitable. The outskirts of galaxies, in the modern universe, are where gas goes to do nothing. It sits there, warm and diffuse, waiting to be swept up by some future interaction or merger. Yet here we are, looking at a region outside one of the most distant galaxies ever observed, a region at redshift 10.6, roughly 400 million years after the Big Bang, and that region appears to be forming first-generation stars, stars that should not exist in that location, stars that should not exist at all according to some earlier models of the first few 100 million years, and yet the spectral data says they are there. The He2 emission says something is burning at over 100,000 Kelvin. The zero metallicity says it is burning from pristine gas, and the spatial offset from GN-Z11 says it is doing all of this in a place that our models would label wrong. The leading explanation for this anomaly is both simple and profound. The HE region may represent a remnant pocket of primordial gas, a reservoir of hydrogen and helium left over from the Big Bang that, through some combination of location, geometry, and circumstance, was never incorporated into GN-Z11 itself. While the galaxy was forming, pulling in gas, building stars, and feeding what appears to be a supermassive black hole, this particular pocket of gas was bypassed. It sat at the periphery, untouched, while the galaxy's own stellar activity was already producing metals and ejecting them into the surrounding medium through supernova winds and radiation-driven outflows. And here is what makes that survival so strange. In most models of early galaxy formation, the circumgalactic medium, the gas surrounding a young galaxy, gets enriched relatively quickly. When massive stars inside the galaxy explode as supernovae, they do not just scatter metals into their immediate surroundings. They drive powerful outflows that carry processed material outward at hundreds or thousands of kilometers per second. These outflows reach well beyond the galaxy's visible boundary, polluting the surrounding gas with carbon, oxygen, silicon, and iron. Radiation fields from hot stars ionize and heat the surrounding medium. Over tens of millions of years, which sounds long to us but is almost nothing in cosmological terms, the zone around an active galaxy becomes chemically contaminated. The pristine era ends. For a pocket of gas to survive this process, to remain at zero metallicity while sitting at the doorstep of a galaxy that is actively producing and distributing metals, something about the local environment must have shielded it. Maybe the outflows from GN-Z11 were directional, blasting metals in one direction while leaving other regions untouched. Maybe an intervening structure, a denser filament of gas, a gravitational ridge in the surrounding medium, acted as a barrier, deflecting the enrichment wave around this pocket, like a rock splitting a stream. Maybe the pocket was infalling from a direction that happened to be upstream of the contamination front, arriving pristine at the galaxy's edge, just as JWST happened to be watching. We do not know which of these explanations is correct. We may never know for this specific region, because the spatial resolution at this distance, a few pixels on a detector, simply does not allow us to map the detailed gas dynamics around GN-Z11 with the precision needed to reconstruct what happened. But the fact that it happened at all, the fact that pristine gas can survive this close to an active galaxy at this epoch, tells us something important about the early universe that extends far beyond this one detection. It tells us that chemical enrichment in the first few 100 million years was not uniform. It was not a smooth, galaxy-by-galaxy phase transition, where each region of the universe progressed neatly from primordial to enriched on roughly the same timeline. It was patchy, uneven, chaotic in the literal, physical sense of the word. Regions of chemical complexity, places where multiple generations of stars had already formed and died, could exist right next to regions of primordial simplicity, where not a single star had yet contributed a single atom of carbon to the surrounding gas. The boundary between the two was not a cosmological frontier separated by millions of light years. It could have been as close as the distance from one gas cloud to the next. This realization upends a certain comfortable picture of early cosmic evolution. The standard narrative: first stars form, they enrich their environment. Next generation of stars forms from that enriched gas. Repeat, implies a kind of orderly progression, a wave of complexity spreading outward from each galaxy, gradually transforming the universe from simple to complex. The location anomaly near GN, Z11, suggests the reality was far messier. The transition from population 3 to population 2 was not a clean phase change, like ice melting uniformly into water. It was more like frost forming on a window, patchy, irregular, governed by local conditions that varied from one pocket of gas to the next. And this messiness has consequences that ripple forward through cosmic history. If population 3 star formation was not confined to the interiors of the first galaxies, if it also happened in their halos, in their accretion streams, in isolated pockets of pristine gas scattered through the circumgalactic medium, then the first stars may have been distributed far more widely than models assumed. Their ultraviolet radiation would have contributed to reionization not just from concentrated galactic sources, but from a dispersed network of formation sites scattered across the early cosmic web. Their supernovae would have enriched not just compact regions, but a broader, more diffuse volume. Their black hole remnants, if the most massive population 3 stars collapsed directly, could have been seeded across a wider range of environments, potentially explaining some of the puzzling distribution of early black holes that JWST keeps turning up. The location anomaly, in other words, does not just make this one detection harder to explain. It suggests that our models of the first few 100 million years, models built on assumptions of relatively smooth, predictable enrichment, may be missing an entire layer of complexity. The early universe may have been a far more heterogeneous place than we thought, with pockets of primordial chemistry surviving in the shadows of galaxies that were already chemically mature. So let me step back and take stock of where we are. We have a signal that shows the hottest radiation ever associated with zero metallicity gas. We have a spatial location that defies standard star formation models. We have a dual-component structure that captures both the pristine and enriched phases of the universe's first chemical transition. We have ruled out black holes as likely sources. We have ruled out Wolf-Rayet stars. We have acknowledged the risk of confirmation bias while noting the independent corroboration that strengthens the case. And we have now added a location anomaly that, rather than weakening the detection, actually makes it more interesting, because it suggests the early universe was wilder and more complex than our models anticipated. Everything about this detection is unusual. The chemistry is unprecedented. The temperature is extreme. The location is, by any conventional standard, wrong. And the timing, catching both the before and the after in the same observation, borders on implausible. Taken together, these anomalies point in one of two directions. Either we are witnessing something genuinely new, a detection that reshapes our understanding of how the first stars formed and where they formed, and how quickly the universe transitioned from simple to complex. Or we are misreading one of the most challenging datasets in the history of observational astronomy, extracting meaning from noise at the ragged edge of what our instruments can deliver. Either way, the implications are enormous. And the biggest one, the one that steps beyond astrophysics entirely, beyond spectra and models and redshift values, into something far more personal, is still ahead. Part 13. The Missing Stars. Here is the fact that should unsettle you. If population 3 stars were the most important stars in the history of the universe, the ones that created the first heavy elements, that drove reionization, that seeded the formation of galaxies and black holes and everything that came after, then you might reasonably expect us to have found at least one by now. Somewhere, a surviving specimen, a relic still glowing, however faintly, from that first generation. Something we could point a telescope at and say, there it is, the oldest star that ever existed, still burning after all this time. We have not found one. And here is the part that should genuinely unsettle you. We never will. Not because our telescopes are not good enough, not because we have not looked hard enough, not because they are hiding in some unobserved corner of the universe waiting to be discovered. We will never find a surviving population 3 star because there are none. They are gone. Every single one of them. Extinct, in the fullest possible sense of the word. The physics is merciless on this point. The same properties that made population 3 stars the most important objects in cosmic history, their enormous masses, their extreme luminosities, their ferocious energy output, also made them catastrophically short-lived. A star with 100 solar masses does not burn for billions of years like our Sunday. It burns for maybe 2 or 3 million years. A star with 500 solar masses might last less than 1 million. A star with 1,000 solar masses, if such objects existed, and the models suggest they did, would have exhausted its nuclear fuel in a time span so short that it barely registers against the age of the universe. A few 100,000 years, maybe less. To put that in perspective, the universe is currently about 13.8 billion years old. 1% of that is 138 million years. Population: 3 stars burned out before the universe had reached even a fraction of that milestone. By the time the cosmos was 1 billion years old, still in its infancy by any standard, every population 3 star that had ever formed was already dead. Every single one had either detonated in a pair instability supernova, obliterating itself completely and scattering its processed elements into the void, or collapsed directly into a black hole, swallowing its own material and disappearing behind an event horizon. There was no middle ground, no graceful retirement, no slow cooling into a white dwarf or a fading red giant. These stars lived fast and died in one of the 2 most violent ways the universe permits. And once they were gone permanently. There is no mechanism to create new population 3 stars in the modern universe. The conditions that produced them, pristine gas with 0 metallicity, large Jeans masses due to inefficient cooling, top-heavy initial mass functions, those conditions existed only in the first few 100 million years after the Big Bang. Before the first supernovae contaminated the surrounding medium with metals, once that contamination happened, even in trace amounts, the physics of star formation changed. Clouds could cool more efficiently. They fragmented into smaller pieces. The stars that formed were smaller, less extreme, longer lived. The era of population 3 was over, and it can never come back. The universe used up its pristine material, and there is no way to unenrich gas once it has been seeded with metals. The arrow points in only one direction. So what remains? Traces. That is all. Chemical fingerprints embedded in the oldest surviving stars in our galaxy, stars that are not population 3 themselves, but that formed from gas only lightly enriched by the first generation's deaths. These ancient stars carry anomalous element ratios that hint at the specific yields of pair instability supernovae, unusual abundances of certain elements relative to others, patterns that do not match the yields of any modern supernova type, but do match the theoretical predictions for explosions of extremely massive, metal-free progenitors. They are forensic evidence, the children testifying about parents they never met, carrying inherited traits that point back to an origin they cannot directly remember. There are also theoretical models, increasingly sophisticated simulations that predict what population 3 stars should have looked like, how they should have formed, how they should have died, and what chemical signatures they should have left behind. These models are constrained by observations, refined by each new measurement, and tested against the growing catalogue of extremely metal-poor stars and high redshift galaxies. They are our best reconstruction of events we cannot observe, built from physics we trust applied to conditions we have never directly witnessed. And now there is possibly one more thing. A spectral signal from a region near GN, Z11, the Head 2 emission with zero metals, captured by JWST and preserved across 13.4 billion years of cosmic expansion. If the interpretation holds, this signal represents the closest we have ever come to directly detecting population 3 stars. Not the stars themselves, they are long dead, but the light they emitted during their brief existence, frozen at a redshift of 10.6 and carried across the observable universe by the expansion of space itself, arriving at an instrument orbiting the second Lagrange point, 1.5 million kilometers from Earth, in a year when the universe is nearly 14 billion years old. Think about what that means. We are not seeing population 3 stars, we are seeing the light they left behind. An echo, a message dispatched 13.4 billion years ago by objects that ceased to exist 13.4 billion years ago. The light has been traveling for the entire history of the universe as we know it, through the era of reionization, through the assembly of the first galaxies, through the formation of the Milky Way, through the birth and death of our sun's predecessor stars, through the collapse of the solar nebula, through the formation of Earth, through the emergence and extinction of entire biospheres, and it arrived at JWST carrying information about a moment so ancient that nothing from that era still exists in recognizable form. It is the astronomical equivalent of reading a message written by someone who died before the ink dried. The sender is gone, has been gone for longer than most structures in the universe have existed. The message survived only because it was written in light, and light, once emitted, does not stop unless something absorbs it. This particular light travelled through 13.4 billion years of increasingly empty space, redshifting from ultraviolet into infrared as the universe expanded around it, growing fainter with every passing epoch, until it landed on a gold-coated mirror floating at a gravitationally stable point in the Earth-Sun system. The message arrived. The sender has been dead for almost the entire history of time, and the message is all we will ever have. This creates an epistemological problem that extends well beyond astronomy. The most important objects in the history of the universe, the ones whose existence enabled everything else, from galaxies to planets to the chemistry of life, are permanently and irrevocably beyond direct observation. We will never image a population 3 star. We will never resolve one as more than an inference. We will never measure its mass by watching its gravitational influence on a companion. We will never track its evolution through spectroscopic monitoring over time. We will never observe its death in real time, the pair instability detonation, or the direct collapse, and confirm our models against direct evidence. Every single thing we learn about these stars will be reconstructed, inferred from chemistry, deduced from spectra, extrapolated from simulations, built from fragments. This is not unprecedented in science. Paleontologists reconstruct entire ecosystems from fossilized bones. Archaeologists infer civilizations from pottery shards and foundation stones. Cosmologists deduce the conditions of the early universe from the statistical properties of the cosmic microwave background. The practice of building knowledge from incomplete evidence is not new, but the scale of what we are attempting here is staggering. We are trying to understand the origin of all cosmic chemistry, the ignition of the process that made the universe transparent, the seeding of the first structures that would evolve into every galaxy in the observable universe. And we are doing it based on some of the faintest, most distant, most ambiguous signals any instrument has ever recorded, captured at the extreme boundary of observational capability from an epoch we can barely resolve. The stakes could not be higher. The evidence could not be more fragile. And yet the JWST detection, if it holds, represents the closest we may ever come. It is a snapshot, not of the stars themselves, but of the moment just before and just after they existed. C1 the universe before the first stellar death. C2, the universe just after, both preserved in the light of a region that was, for a brief cosmic instant, pristine enough to retain the signal and young enough to still be forming its first generation. It is a window into the origin, but it is narrow, it is distant, and it is already closing. Every year, the expansion of the universe pushes these signals further into the infrared. Every year, the photons stretch a little more, grow a little fainter, drift a little closer to the detection limits, even of an instrument as powerful as JWST. The window does not stay open forever. The most important stars in cosmic history are invisible. They left no survivors. They left no remnants we can visit. Their legacy is everywhere, in every heavy element, in every rocky planet, in every molecule of water and strand of DNA. But the stars themselves are gone, and the only direct evidence that they ever existed may be a faint emission line on a spectrograph detected by a telescope that was built over the course of decades, launched on a rocket on Christmas morning 2021, and deployed to a point in space specifically chosen to be cold enough and stable enough to catch the faintest whispers of the oldest light in the universe. That fact alone should make you think, not just about population 3 stars, but about what else might be invisible. What other foundational processes might have occurred in those first few 100 million years and left no surviving witness? What other objects might have existed, briefly, violently, consequentially, and vanished before anyone or anything was around to record them? The universe is nearly 14 billion years old, and for the first several 100 million of those years, it was doing things we can only guess at, building structures we can only infer, running processes we can only model. We are reconstructing the opening chapter of cosmic history from its fading ink. And the next part of this story, the part that reaches beyond astrophysics entirely, is about what those vanishing stars left behind inside you. Part 14. Black Hole Seeds. There is one more legacy these vanishing stars may have left behind, and in some ways it is the most paradoxical one. Because while some population 3 stars died in the most spectacular explosions the universe has ever produced, scattering their processed elements across space and kick-starting the chemical evolution of the cosmos, others may have died in complete silence. No explosion, no flash, no outward sign at all, just a sudden total collapse. The entire mass of a star, hundreds or thousands of times heavier than our sun, folding inward on itself and disappearing behind an event horizon. A black hole, born not from the death of a star, as we typically imagine it, not from a core collapse supernova with its expanding shockwave and its glowing remnant nebula, but from a direct, catastrophic implosion. The star burns through its fuel, the core destabilizes, and instead of bouncing back and ejecting its outer layers, the entire structure falls in. There is no pair instability detonation to blow it apart. There is no neutron star left behind. There is just a region of space-time where a star used to be, now wrapped in a boundary from which nothing, not light, not matter, not information, can escape. The theoretical threshold for this to happen is roughly 260 solar masses, though the exact boundary depends on the models you use and the assumptions you make about rotation, magnetic fields, and the star's internal structure. Below that threshold, but above about 130 solar masses, the star enters the pair instability regime, the runaway process where gamma rays in the core convert to electron-positron pairs. The pressure drops, and the star either detonates completely or undergoes violent pulsations that shed mass before a final collapse. But above 260 solar masses, the collapse is so overwhelming, so total, that the pair instability mechanism cannot reverse it. The star does not explode, it does not pulsate, it simply ceases to exist as a star and becomes a black hole in a single, irreversible event. And here is what makes this matter for the larger story. These black hole remnants would not have been small. A population 3 star with 300 solar masses collapsing directly would leave behind a black hole of perhaps 200 or more solar masses. Depending on how much mass was lost to radiation and stellar winds during the star's brief life, a star of 1,000 solar masses could produce a remnant of several hundred. These are not the stellar mass black holes we detect in our own galaxy, the 10 to 30 solar mass remnants left behind by ordinary supernovae. These are something else entirely. They are seeds, starting points, objects massive enough to serve as the gravitational nuclei around which much larger structures could eventually grow. And this matters because one of the most persistent and uncomfortable puzzles in modern astrophysics is the existence of supermassive black holes at high redshift. Let me put the problem simply. We observe black holes at the centers of galaxies that are billions of solar masses, objects so massive that their gravitational influence shapes the motion of stars across an entire galactic core. In the nearby universe, these are not surprising. Galaxies have had nearly 14 billion years to build up their central black holes through accretion, mergers, and the steady consumption of surrounding material. Time is the explanation. Given enough time, even a modest seed can grow into a monster. But JWST and other observatories keep finding supermassive black holes at redshifts that correspond to the first billion years of cosmic history. Black holes that appear to contain hundreds of millions or even billions of solar masses, existing at epochs when the universe was barely old enough to have formed its first galaxies. The black hole in GN Z11 is one example, present at just 400 million years after the Big Bang, already massive enough to power an active galactic nucleus. And it is not alone. Over the past several years, a growing catalogue of high redshift black holes has emerged, each one raising the same question: how did they get so big, so fast? Standard accretion models struggle with this. If you start with a seed black hole of, say, 10 solar masses, the kind left behind by an ordinary supernova in the modern universe, and let it accrete material at the maximum theoretical rate, a limit called the Eddington rate, which balances the inward pull of gravity against the outward push of radiation pressure from the infalling material, it takes a very long time to reach 1 billion solar masses, longer than the universe had been around when these black holes are observed. The math simply does not work. You either need more time than the universe provides, or you need to break the Eddington limit for sustained periods, which is theoretically possible but physically difficult to maintain, or you need a bigger seed. Population. 3 stars provide exactly that. If the first generation of stars included objects in the range of several hundred to 1,000 solar masses, which is precisely what the primordial gas physics predicts, with its inefficient cooling and top-heavy initial mass function, then the black hole remnants they left behind would have been orders of magnitude more massive than anything produced by modern stellar evolution. A seed of 200 solar masses has an enormous head start over a seed of 10. It needs fewer doublings. It reaches 1 million solar masses faster. It can plausibly grow to 1 billion solar masses within the available time, even without exotic super Eddington accretion episodes. And these seeds would have formed early, very early. Within the first 100 million years after the Big Bang, the most massive population 3 stars would have already completed their entire life cycles and collapsed. By the time GN Z11 was assembling itself at 400 million years, the black hole seeds from the earliest population 3 generation could have been growing for 200 or 300 million years already. A significant head start that makes the existence of a supermassive black hole at this epoch far easier to explain. The black hole in GN Z11 fits this picture with uncomfortable precision. Its presence at redshift 10.6 in a system that also shows evidence of first-generation star formation in its immediate vicinity is exactly what you would expect if population 3 stars were producing both chemical enrichment through supernovae and black hole seeds through direct collapse, simultaneously in the same epoch. The stars that exploded gave the universe its first metals, visible now as the faint enrichment in C2. The stars that collapsed gave the universe its first massive black holes, visible now as the active nucleus of GN, Z11 itself. Two different death pathways from the same population, producing two different legacies that we can observe in the same system 13.4 billion years later. And if this picture is correct, then the implications extend far beyond GN Z11. Every large galaxy in the observable universe, including the Milky Way, has a supermassive black hole at its center. If those black holes grew from seeds planted by population 3 stars, then the first generation of stars did not just create the elements that make up planets and life. They also created the gravitational anchors around which all galactic structure organized itself. The black holes that shaped the formation and evolution of galaxies, that regulated star formation through feedback processes, that powered quasars and active galactic nuclei across cosmic history. All of them may trace their origins back to the silent deaths of stars that burned from pristine gas in the first few 100 million years. Even in death, even in the most silent, invisible form of death the universe allows, population, 3 stars may have shaped the architecture of everything that followed, the galaxies we see, the structures we map, the cosmic web that connects them, all of it potentially anchored by remnants of objects that no longer exist, that left no light, no chemical signature, no outward evidence of their passing, just gravity, just the permanent warping of space-time left behind when something enormously massive collapses past the point of no return. There is something almost poetic about that, in a way I did not expect when I started researching this. The most visible legacy of population 3 stars, the elements, the metals, the chemistry, came from their most violent deaths, the supernovae that tore them apart and scattered their contents across space. But their most structurally important legacy, the gravitational seeds that organized the universe into galaxies, came from their quietest deaths, the ones where nothing escaped, the ones where the star simply vanished, leaving behind only a dent in the fabric of space that would grow, over billions of years, into the engine at the center of a galaxy. The first stars shaped the universe twice, once through what they released and once through what they kept. And that brings us, finally, inevitably, to the implication that has been building since the beginning of this story, the one that is not about black holes or spectra or redshift values, the one that is about you. Part 15. You are made of this event. I want to bring this back to something concrete, because it is easy, dangerously easy, to let the scale of cosmology turn everything into abstraction. We have been talking about billions of years, billions of light years, temperatures in the hundreds of thousands of Kelvin, masses measured in hundreds of solar equivalents, redshifts so extreme that the light we are analyzing has been traveling since before the Milky Way existed. The numbers get so large, so far removed from anything in daily experience, that they stop feeling like they mean anything. They become wallpaper, scientific decoration, something you nod at and move past. So let me bring it down to the smallest scale I can. Let me bring it down to you. You are made of atoms. That is not a simplification or a metaphor. It is a precise physical statement. Your body is a collection of roughly 7 octillion atoms. That is a 7 followed by 27 zeros, organized into molecules, organized into cells, organized into tissues and organs and systems, that, taken together, produce a person capable of sitting here and listening to someone talk about the first stars in the universe. And those atoms have a composition. Roughly 65% of your body mass is oxygen, 18% is carbon, 10% is hydrogen, 3% is nitrogen. The remaining few percent is a mix of calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iron, and a few dozen trace elements. That is the recipe. That is what you are made of, if you strip away every layer of complexity and look at the raw ingredients. Now here is the part that connects everything we have talked about tonight to you, personally, physically, chemically. Every one of those atoms, except hydrogen and even some of the helium, was produced inside a star. Not metaphorically, not as a poetic way of saying we are connected to the cosmos. Literally, the oxygen atoms in your lungs right now were manufactured through nuclear fusion inside a stellar core, where carbon nuclei were smashed together at temperatures exceeding 1 billion Kelvin until they merged into oxygen. The iron atoms in your hemoglobin, the molecules that carry oxygen through your bloodstream, were the endpoint of a fusion chain, so demanding that it consumed more energy than it produced, destabilizing the core of the star that made them and triggering the supernova that scattered them into space. The calcium atoms holding your skeleton together were forged in the final seconds of that explosion, created in the brief, violent nucleosynthesis that occurs as the supernova shockwave rips through the star's outer layers. Every element in your body has an origin story, and every one of those stories takes place inside a star that no longer exists. But here is what makes the JWST detection near GN Z11 different from the general statement that we are made of star stuff. That phrase, popularized by Carl Sagan, is beautiful and true, but it is also vague. It gestures at a cosmic connection without specifying when or where or how that connection began. It tells you that your atoms came from stars, but it does not tell you which stars, or when those stars first appeared, or what the universe looked like before they existed. The JWST signal tells you that there was a time, a specific, finite, measurable interval in the history of the universe when none of the elements that make up your body existed anywhere, not on any planet, because there were no planets, not in any nebula, because no star had yet died to create one, not in any corner of any galaxy, because the galaxies themselves were barely beginning to assemble. The periodic table, as it existed in the first few 100 million years after the Big Bang, had 2 entries, hydrogen and helium. A trace amount of lithium, produced during Big Bang nucleosynthesis, rounds out the list, and that was it. That was the entire chemical vocabulary of the universe. 2 elements, neither of which, on its own, can form a rock, a liquid, an organic molecule, or anything remotely resembling the chemistry that makes life possible. The universe was full of matter. It was not empty, but it was chemically sterile, incapable of producing complexity, incapable of building structures more elaborate than a cloud of gas. No minerals, no water, no amino acids, no proteins, no DNA, no cells. The raw materials for all of those things simply did not exist yet. They had to be manufactured, and the factories that manufactured them were the first stars. When the first population 3 star completed its fusion chain, hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron, and then detonated in a pair instability supernova, spraying those products into the surrounding void, it was the first time those elements had ever existed in the history of reality. Not the first time we had observed them, not the first time they appeared in a particular region, the first time anywhere, period. The first carbon atom in the history of the universe was synthesized inside one of these stars. The first oxygen atom, the first silicon atom, the first calcium atom. They were new, unprecedented. The universe had never contained them before, and after that moment, it would never be without them again. Those first heavy atoms, scattered into pristine gas by the first supernovae, became the seed material for the next generation of stars. And the generation after that, and the generation after that. Each cycle processed the material further, creating heavier elements, distributing them more widely, building up the chemical complexity of the interstellar medium until, roughly 9 billion years later, a cloud of gas in an unremarkable arm of an unremarkable spiral galaxy had accumulated enough heavy elements to form not just a star, but a disk of debris around that star, and within that disk, enough silicon and iron and oxygen and magnesium to form rocky planets, and on at least one of those planets, enough carbon and hydrogen and oxygen and nitrogen and phosphorus and sulfur to form self-replicating molecules, and eventually cells, and eventually organisms, and eventually, after another 4.5 billion years of evolution, the chain is unbroken. It is physical. It is traceable. Every atom of carbon in every cell of your body descended, through billions of years of stellar recycling, from carbon atoms that were first created in the fusion cores of early generation stars. And those early generation stars descended from the first generation, the population 3 stars that the JWST signal may be showing us. The connection between the He2 emission line detected near GN Z11 and the atoms in your body is not symbolic. It is genealogical. You are the downstream product of a chemical process that began in a specific place, at a specific time, in a specific event. And that event is what JWST appears to have captured. The C1 component, with its zero metallicity, is the universe before your atoms existed. The C2 component, with its faint trace of metals from the first supernova, is the universe in the first moments after your atoms began to be created. The transition between them, visible in the same spectral observation, separated by a velocity offset of 120 kilometers per second, is the moment the universe became capable of eventually producing you. And the terrifying part, the part that I think genuinely earns that word in the title, is not the scale. It is not the distance, or the time, or the temperatures involved. It is that this origin, your origin, rests on something we cannot fully see. The stars that initiated the chain are extinct. Every single one. Their environments are beyond our spatial resolution, a few pixels on a detector, 13.4 billion light-years away. The physics of their formation, while predicted by theoretical models for over 50 years, has never been reproduced in a laboratory, never observed in controlled conditions, never confirmed by anything other than indirect inference, and now, this one spectral signal from the edge of the observable universe. We are descended from objects that are permanently inaccessible to us, objects whose existence we can infer but never confirm directly, objects whose properties we can model but never measure, objects that burned so briefly and so long ago that the only trace of their existence is a pattern of photons that has been traveling through expanding space for 13.4 billion years, growing fainter and redder with every passing epoch until it arrived at a telescope orbiting a gravitationally stable 0.1.5 million kilometers from Earth, a telescope that was designed, funded, built, launched, and deployed over the course of decades, in part to answer this exact question. You are the consequence of a cosmic event so ancient that its perpetrators are gone, so violent that it reshaped the chemistry of the entire universe, so brief that it lasted only a few million years in a cosmos that has existed for nearly 14 billion, and so fragile in its evidence that we detected it as a faint emission spike on a spectrograph captured by an instrument floating in the cold silence of deep space, staring at a smudge of light from an era when the universe was younger than some mountains on Earth. That is not just a discovery. That is a reckoning with what we are and where we come from, told not in mythology, not in philosophy, not in metaphor, but in the wavelengths of light from the edge of observable time. And it means that the next time you look at your hand, or take a breath, or feel your heart beat, you are experiencing the long-delayed consequence of something that happened 13.4 billion years ago, in a pocket of pristine gas at the outskirts of one of the first galaxies, where stars that no longer exist burned with a fury the universe has never repeated. That is what the JWST signal means. Not for astrophysics, for you. Part 16. The hunt is over, or just beginning. The James Webb Space Telescope may have done what it was built to do. That sentence deserves a moment, because it is easy to let it slide past as a simple statement of fact. But think about what it actually represents. JWST was conceived in the 1990s. It was designed through the 2000s. It survived budget crises, political battles, engineering setbacks, and a development timeline that stretched so long some of the scientists who originally proposed it retired before it launched. It was folded into a rocket, sent 1 million miles from Earth, and unfolded, a process involving hundreds of single points of failure, any one of which could have ended the mission, in the cold silence of deep space. It reached its orbit at the second Lagrange point on January 24, 2022, and began collecting data a few months later. And, within its first few years of operation, it captured a spectral signal from a region near one of the most distant galaxies ever observed that matches, in detail, the prediction that motivated a significant portion of the telescope's design: the detection of He2 emission in a zero metallicity region near GN Z11, consistent with population. 3 star formation represents the strongest candidate ever recorded for direct evidence of the universe's first generation of stars. If the interpretation is confirmed, it closes a chapter of astrophysics that has been open since the 1960s. More than half a century of theoretical prediction, observational searching, instrument development, and incremental progress, all converging on a single emission line in a single spectrograph from a single region at the edge of the observable universe. But confirmation is not here yet, and that distinction matters more than it might seem. This is a single detection, one region, one galaxy, one instrument, one observing program. The signal is real, confirmed by companion detections and supported by independent analysis. The interpretation is consistent, matching theoretical predictions that have been refined for decades. The alternatives have been examined and found wanting. But in science, consistent and confirmed are not the same word, and the distance between them is measured in replications. To elevate this from the strongest candidate to an established discovery, the astronomical community needs something it does not yet have: independent verification from separate sources. Other pristine He2 emitting regions, found near other high redshift galaxies, at other redshifts, observed through separate programs and analyzed by different teams using independent pipelines. The signal needs to be reproduced. The interpretation needs to survive, not just the scrutiny that has already been applied, but scrutiny from angles that no one has thought of yet. Because in science, at the frontier, the thing that overturns a result is almost never the objection you anticipated. It is the one that comes from a direction nobody was watching. JWST itself will be a major part of that verification effort. The telescope has years of operational life remaining, and future observing cycles can target additional high redshift galaxies, objects at similar redshifts to GN Z11, or even higher, searching for similar spectral signatures in their halos, their outskirts, their circumgalactic environments. If pristine gas pockets capable of forming population, 3 stars existed near GN Z11, they should have existed near other early galaxies as well. Finding even one more example would dramatically strengthen the case. Finding several would make it nearly airtight. And JWST's instruments can also be pushed to study the existing HE region in greater detail, measuring the signal at additional wavelengths, constraining the temperature and density of the emitting gas more precisely, testing whether the zero metallicity measurement holds under tighter analysis with longer exposure times and different spectral configurations. Beyond JWST, the next generation of ground-based telescopes is approaching completion, and their capabilities will complement Webb's in ways that matter directly for this science. The extremely large telescope, currently under construction in the Atacama Desert in Chile, will have a primary mirror 39 meters in diameter, 6 times wider than JWST's. The 30-meter telescope, planned for Mauna Kea in Hawaii, and the giant Magellan telescope, also in Chile, will bring similar or complementary light-collecting areas. These instruments will operate at optical and near-infrared wavelengths, with adaptive optics systems that compensate for atmospheric distortion, achieving angular resolutions that rival or exceed space-based observatories. They will be able to study objects at redshifts comparable to GN, Z11, with techniques that JWST cannot employ: higher spectral resolution, different wavelength coverage, and the sheer photon collecting power that comes from mirrors measured in tens of meters rather than 6.5. The combination of JWST in space and these ground-based giants on Earth will create a toolkit for studying the early universe that is qualitatively different from anything available today. Structures that JWST resolves as a few pixels could be mapped in detail. Spectral features that are marginal in current data could be measured with precision. And the critical question, whether the He2 signal near GN Z11 is a unique anomaly or the first example of a common phenomenon, could be answered within the next decade. And if that answer is yes, if population 3 stars are confirmed to have existed, then the science does not end. It transforms. The question pivots from "do they exist?" to "what exactly are they?" And that second question contains an entire generation of unknowns, each one representing its own research program, its own set of observations, its own potential to reshape our understanding of early cosmic evolution. We do not know the masses of population 3 stars with precision. The models predict a range, tens to thousands of solar masses, but the actual distribution, the shape of the initial mass function, has never been measured. We do not know their lifespans with certainty. We do not know whether they formed primarily in isolation, single massive stars igniting alone in primordial gas clouds, or in clusters, the way the C1 and C2 components near GN Z11 seem to suggest. We do not know how their supernova yields, the specific amounts and ratios of elements they produced, compare to theoretical predictions. We do not know whether they were the dominant drivers of reionization or merely contributors alongside other sources like early galaxies and accreting black holes. We do not know how many of them collapsed into black holes versus how many exploded, and we do not know how that ratio varied with mass, environment, and epoch. Each of those unknowns is not a footnote. Each is a question large enough to sustain entire careers, entire observing programs, entire theoretical frameworks. The detection of population 3 stars, if confirmed, does not close the book on the first stars. It opens it. Everything before this moment was the preface, the search, the prediction, the decades of "we think they existed, but we cannot find them." Everything after is the actual story, the characterization, the detailed understanding, the slow, painstaking work of turning a detection into knowledge. That is the inflection point we may be standing at right now, the moment where the field pivots from hunting for the first stars to studying them, from asking whether they were real to asking what they were like. It is the difference between knowing that a continent exists and mapping its coastline, its rivers, its mountains, its interior. The first step is dramatic. The second is where the real understanding lives. And there is something larger here, something that reaches past the specifics of He2 emission and metallicity flaws and pair instability supernovae and initial mass functions. Something about the nature of the question itself. For most of human history, the question of where we came from, where the material world originated, where the substances that make up our bodies and our planet and our sky were first created, was answered by mythology, by philosophy, by religion. Every culture had its origin story, its account of how the world was made, its explanation for why there is something rather than nothing. These stories were not science, but they were responses to the same fundamental question that drives this research. How did all of this begin? The scientific version of that question, where did the elements come from, was not even askable until the 20th century, when nuclear physics advanced far enough to explain stellar fusion. It was not traceable to its cosmic origins until observational astronomy reached the point where we could study objects at high redshift and connect their chemistry to the predictions of nucleosynthesis theory. And it was not testable, not directly, not with a specific spectral signature from a specific epoch, until the James Webb Space Telescope captured the He2 signal from the HE region near GN Z11. If this detection is what it appears to be, it connects the present moment to the very first moments of chemical creation. It draws a line, a literal, physical, traceable line, from a spectrograph orbiting a Lagrange point to a cluster of massive, dying stars in a pristine gas cloud 400 million years after the Big Bang. And along that line runs everything. Every generation of stars, every supernova, every accretion disk, every collapsing cloud, every planet that ever formed around any star, every ocean, every cell, every living thing that has ever existed on any world, in any galaxy, across 13.4 billion years of cosmic evolution. The universe hid its origin in light, ancient, red-shifted, stretched to the edge of detectability, and sent it to us across 13.4 billion years of expanding space. We built a telescope. We placed it 1 million miles from home. We pointed it at a tiny patch of ancient sky, and we found, in a faint spike of ionized helium from a region outside one of the first galaxies, what appears to be the fingerprint of the moment everything began. The hunt may be over, but what we are looking at, the scale of it, the strangeness of it, the sheer improbability that we are here at all, that matter, assembled itself into beings capable of detecting the moment of its own creation, is just now coming into focus. And honestly, that is the most terrifying part of all of this. Not what we found, not the signal, not the stars, not the chemistry, but how much is still out there. How many other signals are traveling through expanding space right now, carrying information about events we have not imagined, from epochs we have not yet reached, written in wavelengths of light we have not yet learned to read. The first stars were hidden for 50 years. We found them, maybe, with the most advanced instrument ever built, pointed at exactly the right place, at exactly the right time. What else is the universe hiding? And what will it take to find it? That question, I think, is worth sitting with, because the answer is not just about telescopes and spectrographs and funding cycles. It is about whether we, as a species, will keep looking, whether we will keep building instruments capable of reading messages that have been traveling since before our planet existed, whether we will keep asking questions whose answers take decades and billions of dollars and entire careers to find. The first stars burned for a few million years and then vanished. Their light survived, and 13.4 billion years later, that light found us. The least we can do is keep watching.